to take this opportunity to thank everyone for attending the webinar today. I'm delighted to have you all here today. Before we begin, I would like to introduce myself. My name is Yaman Vadwani, and I work as an international sales manager for Sophistic UK. I'm here with Deepak Prajapati, who works as one of the directors at Post Structural Engineers. And during the course of the webinar, if you have any questions, please feel free to write them in the questions box. I think you can see my. Next slide. So here's the agenda for today. I'll briefly take you to the company overview, and Deepak will then introduce you to the basics of analysis of cable stayed bridges. That would be the main focus for today. I will then, if we have time, show you some project examples followed by questions and answers.
Kalau aku mikirnya Pak ya, itu kalau semuanya ada 3 kalau gitu.
Like many finite element software developers, we are a university spin-off too. We have been in this market for a very long time. It's been more than 3 decades, actually. So, and we have offices around the globe. We are headquartered in Germany with our main offices in Munich and Nuremberg. In the rest of the world, we have offices, for example, in the UK, where I'm based, and we have offices in Austria and so on. We are an Autodesk industry partner, and you will find that some of our products are very closely aligned with Autodesk products. We have an international presence and an extensive network of resellers and distributors in more than 30 countries. Some of our clients would include the likes of AECOM, Sistra, Rambo, and more. The good news about Sophistic is that it can be used for any type of structure. I call it as a single Sophistic environment that can be used for analysis and design of any type of structure, such as buildings, bridges, tunnels, membrane type of structures, and so on. We provide full functionalities for these structures. For example, for membrane type of structures, we provide form finding features which are important for membrane structures. And for bridges, we provide bridge loading. So what I'm trying to say here is that we provide features that you expect for design of all these type of structures. For geotechnicals or soil structure interaction, we have quite strong capabilities. There are various options from simple to advanced solutions. Like most software, you can model soil springs or nonlinear springs. But in Sophistic, you can also define soil layers, and the program will automatically work out equivalent springs for you. You can also model soil as continuum, and we support common material models such as Moore Coulomb. We are very strong in BIM capabilities, and our seamless workflow allow you to model, analyze, design, and do the rebar detailing within the Revit environment. You can use Sophistic to analyze and design any type of bridge, from simple bridges such as slab bridges or beam slab bridges to advanced bridges such as cable stayed and suspension bridges. Today's focus is theory of cable stayed bridges. So I would now like to hand it over to Deepak to take it from here.
Thank you, Yaman, for transferring the stage to me. I hope my screen is visible to everyone. So, hello everyone. Thank you for attending today's webinar.
Yeah, I can see your screen.
Okay, Yaman, thank you. I am Deepak Prajapati. I am Director at Post Structural Engineers Private Limited, and we are based in Mumbai, India. So today, I will introduce you to analysis of cable stayed bridges. So let's get started. So coming to the topics to be discussed today, Well, it's a huge topic. So, given the limited time of webinar, I will cover only the analysis procedure for static load effects only. And I will not go into wind and earthquake related dynamic analysis. Also, I will be focusing majorly on the concrete bridges, but will give some information regarding steel bridges here and there. So first, I am going to start with a little introduction about cable stayed bridges. In here, I am going to cover what is their economic span range. Next, I will talk about their structural behavior. Next, I will talk about their special advantages. And next, I will try to explain what makes them so difficult to analyze. In here, I will first talk about the high level of statical indeterminacy attached with them and how the relative stiffness of elements can affect the load paths because of it. Next, I will talk about the nonlinear effects that we need to take into account in the analysis. Next, I will take you through the design process. In here, first I will list the design steps that we need to follow to analyze and design the bridge successfully. Next, I will explain each design step in detail with the help of a few concept level examples where applicable. I will start with the selection of geometry and deck material and section. Then I will move on to the preliminary calculations for initial section selection. Then I will move on to the construction stage analysis, where I will talk about the backward and forward construction stage analysis. And then finally, I will move on to the final live load analysis. So, coming on to the economic span range. The position of the cable stayed bridge, as can be seen in this figure, falls between arc bridge on the left and suspension bridge on the right. On the x-axis, we see here the center span. On the y-axis, we see the cost per meter square of the deck. Thus, the economic main span of cable stayed bridges lies between 100 meter and 1100 meter. For 100 meter, we should be going with one pylon, and for 1100 meter, we should be going with two pylons. So, let's take a look at the structural behavior of cable stayed bridges. In cable stayed bridges, the deck is supported by cables. As the deck transfers the dead load and the live load which acts on it to the cables, and the cables transfer the load to the pylon in tension. Then pylon transfers the load to the ground in compression. As we can see here, the blue color represents compression and the red color represents tension. We can also see that the deck is also in compression due to the horizontal component of the cable load, which is generally balanced on either side of the pylon. So this force eventually balances this one, and this force eventually balances this one. The pretension in the cable is adjusted in such a way that the deck behaves as rigidly supported over cables for permanent loads, and it behaves elastically supported for live loads. So, what are the advantages of cable stayed bridges? First of all, the bending moment in the deck is highly reduced. As explained in the previous slide, by pre-tensioning the cables, the deck can be made to behave as rigidly supported over cables. As can be seen in this example, over here we have a continuous beam supported over three piers. The bending moment of the beam for permanent load is shown here. Now, for the same continuous beam, by inserting two cables and pre-tensioning them, we can make the beam to behave as if two extra supports have been provided. And thus, the bending moment for permanent loads is highly reduced. Even for live loads, the beam will behave as if it is elastically supported over the stay cables, and hence the live load bending moments will also remain small. The second important advantage of cable stayed bridge is the large compression force in the deck, as we had seen in the previous slide, sorry. That is caused by the horizontal component of the cable force. For concrete decks, this compression force is very beneficial as it reduces the amount of steel or pre-stress required to counter the bending moment in the deck. So, the third important advantage of cable stayed bridge is their ease of construction. Cable stayed bridges can be easily constructed by following the free cantilevering method. They are inherently stable during construction process and do not require temporary supports. On the other side, if we see arch bridges, they are not stable during erection until the arch is closed and the horizontal support forces are anchored. They have to be temporarily supported, as we can see over here, by auxiliary piers or temporary tiebacks. Also, self-anchored suspension bridges, which are required when the horizontal cable component cannot be economically anchored due to the bad soil condition into the ground. So generally, in suspension bridges, the cables are anchored into the ground. So, the self-anchored suspension bridges will also need temporary supports of their beams until the main cables are installed and the beam is closed. The fourth main advantage of cable stayed bridges is that they are inherently stiffer than suspension bridges. This is especially true for longitudinally eccentric loads. For longitudinally eccentric loads, the main cable of the suspension bridge finds a new equilibrium without any increase in the cable stresses. For example, if I place a concentrated load over here, the deflected shape of the cable will change to account for the concentrated load, and there will be no increase in the cable stress. And if I place the concentrated load here, again the stress in the cable will remain same. However, in cable stayed bridges, the cables have always to be additionally stressed in order to carry any load. Hence, suspension bridges are thus generally not suitable for high railway loads since their deformations become too large, whereas cable stayed bridges serve the purpose well. So, coming on to the next slide, why is it so difficult to analyze cable stayed bridges? Why can't they be analyzed like simply supported girdle bridges? Well, the first answer to that is the high level of statical indeterminacy associated with them. In statically determinate systems, the load path or load sharing between member is independent of the relative stiffness of the member. However, in a statically indeterminate system, the load path depends on the relative stiffness of the elements. This can be understood easily with this example. Here, we have a simply supported beam and we have two beam cross sections. So, this is a thicker beam and this is a thicker cross section and this is a thinner cross section. So, if we apply a vertical load in between of P for a simply supported beam, the reaction on the support will always be P by 2 and P by 2 irrespective what is the relative stiffness of these two beams. So for example, if I make this beam even more thicker, the reaction over here will be P by 2 only. However, if we have a fixed beam, so this is a statically indeterminate system, and we apply a vertical load at the center, the reaction on the left hand side, where we have the thicker beam, will be higher compared to the reaction on the right hand side. And these reactions, they will keep on changing as we change the relative stiffness of these two sections. So, coming on to the next slide, we can see that the relative stiffness of the deck and cables is what creates the difference in balanced cantilever, extra doors, and cable stayed bridges. Balanced cantilever bridges have no cable stiffness or and a very high deck stiffness. Now, as we increase the cable stiffness and decrease the deck stiffness and make them of the same order, we have an extra dose bridge. And as we further increase the cable stiffness and decrease the deck stiffness, we will have cable stayed bridges. In cable stayed bridges, the change in the relative stiffness of the cables will also change the load sharing in the cables and the pattern of bending moment in the deck. So basically, if I change the stiffness of this particular cable, this will change the load in all these three cables and it will also change the pattern of bending moment in this particular deck. Hence, it is really very important to choose the right relative stiffness of the cables and the deck at the start to converge onto a required solution of desired bridge behavior. So, coming on to the next slide, nonlinear effects. In addition to the statical indeterminacy that we talked about previously, the nonlinear effects like cable sag, P-delta, and large deformation increase the analysis effort. The sensitivity of the bridge to these effects varies with span range and stiffness of the deck. The longer the bridge and lesser the deck stiffness, more it will be prone to these effects. This is an important consideration to be done because the linear method like influence line method, which is based on elastic superimposition of stiffness and loads, can be used just as a preliminary or approximate method for determining the design loads in the elements. In addition to that, for concrete bridges, the nonlinear material properties like creep and shrinkage can sometimes consistently affect the calculation and determination of the design loads and increase the level of convolution of the calculations and hence the number of iterations required. Hence, as it is generally said, the name of the game for cable stayed bridges is iteration. Taking the nonlinear effects into account and doing so many iterations is not possible by hand calculations. Hence, we need modern softwares like Sophistic. They make accounting for nonlinear effects easy, reduce the time required for iterations, and help us greatly to arrive at a desired and economical solution. So, coming on to the next slide, let's talk about the cable seg effect. To understand the cable seg, let us take an example. If we have a cloth line and we want to tie it horizontal, it is easier to pull the line initially when the sag in the line is very high. But as the sag reduces, the amount of force required to pull the line by the same amount of horizontal distance keeps on increasing. That is, the cable stiffness keeps on increasing with reduced cable sag. Basically, the axial stiffness of an inclined cable is not fixed as compared to a straight vertical cable. It gets reduced with increase in cable sag and vice versa. The effective stiffness of the cable is given by the formula by Ernst that we can see over here. It is important to note that as the cable length increases and weight increases, where Lk represents the cable length and gamma represents the weight of the cable, uh, density of the cable, increases, the sag effect increases, and as the stress in the cable, sigma, what we see over here, increases, the sag effect decreases. The length and weight of the cable is constant in a cable stayed bridge, but the cable stresses can see a large variation for live loads and during construction. From the formula, it can be seen that the cable stiffness varies to the third power of the cable stress. As the cable stress increases, the variation in the cable stiffness for further increase in cable stresses reduces, and hence the nonlinear effect reduce. Hence, it is imperative to use high cable stresses. Also, the stiffness of the cable stayed bridges is governed by the stiffness of the stay cables. Hence, higher steel stresses will result in the higher stiffness of the bridge. The importance of high steel stresses make the use of high strength steel imperative. For strengths with ultimate strength of 1860 MPa, a cable stress of about 680 MPa can be used for the permanent load stage. For such steel stresses, the variation of cable stiffness for live loads will be small. Hence, the nonlinear effects will be small and the cable stiffness will be higher, which will result in lower deflection for live loads. And that is one of the reasons, like why can't we use normal reinforcing steel as cables or tension elements in cable stayed bridges. So, coming on to the next slide, Let's talk about P delta and large deformation effect. Since the deck and the pylon both are in high compression for permanent loads, as we had seen over here, second order moments due to P delta effects are generated in them due to the deflection caused by the live load. The second order moments increase with the slenderness of the beam and can be significant for a slender beam and pylon, and hence should be considered in the analysis. For the same reason, concrete decks are generally less susceptible to P delta effects compared to steel decks. Large deformation effects correspond to the geometric nonlinearity caused due to shift in the line of action of axial forces due to large deflection of elements compared to the initial assumed line of action of force. This effect can also come in the deck of long span cable stayed bridges if the deck deflections are high. But these effects are always applicable to the cables due to their sag. The sag in the cable changes the line of action of the force in the cable. So we can see over here, if we have a cable from here to here, and if we do a linear analysis, the cable element will be modeled as straight from this point to this point. So in that model, the line of action of the cable force will be the line shown in green. However, in reality, the cable will sag due to its own weight, and the actual line of action of cable force will be the one which is shown in the blue. This geometric nonlinearity can affect the design forces in elements significantly and should be considered in the analysis. Okay, now, since we know all the effects that make the analysis of cable stayed bridges difficult, let's move on to the design process. Since a lot of iterations are required to converge onto the required solution, the correct starting point for start of iteration is very important. It can greatly reduce the number of iterations required. Also, very important is the process followed to converge onto the solution. Generally, if we follow this design process, we can relatively easily convert onto the bridge and element configuration that will serve the purpose of the design. So the first step is to use thumb rules to select the geometrical parameters such as backspan to mainspan ratio and pylon height about deck. Then select the cable spacing and deck cross section based on the construction and functional requirements. And then select the deck material based on the span length. The next step is to do hand calculations or some preliminary calculations to determine the cable, deck, and the pylon forces for permanent and live loads. Based on these initial forces, we can estimate the cable and pylon section and can refine the deck section chosen in step 1.
Halo.
Once we have the initial geometry and sections finalized using the previous step, we can go for construction stage analysis. The first step before construction stage analysis is the cable force determination for the final system. After that, the construction stage analysis is done for assessing the necessary pre-camber of the deck to keep it in desired configuration for permanent loads. For assessing the loads in the members during construction and for checking and controlling the real-time erection procedure. There are two approaches for construction stage analysis, namely backward and forward construction stage analysis. Once we have done the construction stage analysis and have the bridge in final configuration for permanent loads, we can do the final live load analysis to get the final section forces and can check the sections we had chosen initially for adequacy as per relevant codes. If everything is good, we have successfully analyzed and designed a cable stayed bridge. Else, we can refine the sections as per requirement and repeat the step 3 and 4 again. So now, let's see the design steps in detail. Step 1. Selection of geometry and deck material and section. The geometry of the cable stayed bridges is determined by the ratio of the side span to main span and tower height above the deck level to the main span. A good ratio is important for an economic design of cable stayed bridges. The ratio between side span and main span influences strongly the stress change in the backstay cables, the one we see over here. Live load in the main span, if we place live load over here, increases the stress in the backstay, while live load in the side span will increase the stress in the backstay. Hence, the fatigue stress variation in the backstay will increase in the ratio of backspan to main span. On the other hand, the increasing span ratio decrease the previously I said wrong. So basically, the fatigue range variation will decrease in the ratio of the backspan to main span, and on the other hand, the increasing span ratio will decrease the vertical uplift anchor forces in the outer anchor piers. So, if we increase the span ratio, we will have benefit in the fatigue range, and if we decrease the span ratio, we will have the benefit in the anchor forces. So for concrete road bridges, the ratio between the live load, so if we see for concrete road bridges, typically the ratio between the live load and dead load often comes to about 0.25. For this live load to dead load ratio, a span ratio of 0.4 for a typical main span of 400 meter gives the same amount of cable steel required for maximum cable load and fatigue range. Hence, generally, For concrete bridges, a typical span ratio of 0.4 is economical. Similarly, for steel railway bridges, the ratio of live load to dead load is about 0.6, and hence a typical span ratio of 0.3 is economical. Coming to the ratio of pylon height to the main span. High pylons reduce the required amount of cable steel and the compression force in the bridge deck up to a cable inclination of 45 degrees, but also increase the cost of the pylon themselves. Optimizations that have been done indicate that the pylon height of about 1 divided by 5 to 1 divided by 6 of the main span achieves minimum cost for the whole bridge. So coming on to the next slide, selection of the cable spacing. The cable spacing should be kept as minimum as possible. Small cable spacing results in one cable for each stay, and the anchorages at the tower and at the beam become more simple. Small cable spacing also reduces the required capacity of the gantry used for construction using free cantilever method. Small cable spacing also results in small bending moments in the deck due to dead load, which reduces the depth requirement and can create an overall economy for the bridge. So, the small cable spacing also results in the reduction of deck and pylon moments and cable force variation during construction. So in this example, we can see if we have a cable stayed bridge and with only two cables, the deck will behave to be supported on 3 points for permanent loads, and hence we will have this bending moment profile. However, if we add two more cables, the deck will behave as it is supported on 5 points for the permanent loads, and the bending moment in the deck will reduce. Coming to the section of the deck, it is economical to choose a small depth for the deck. The depth of the deck is merely independent of the span length since the deck is supported by the cables. The live load movements in the deck are mostly restrained movements which decrease with the depth of the deck. Hence, it is beneficial to reduce the depth of the deck. However, the deck should be safe for buckling. At this step, the initial deck cross section should be chosen based on experience and functional requirements such as the deck width to carry the live load, number of planes of cable, minimum depth requirement if any. The selected deck section should be refined as per the preliminary forces calculated that will be calculated in step 2. Regarding material of the deck, as a rule of thumb, concrete deck sections are suitable for span range from 200 to 400 meters. Composite decks are suitable from 400 to 600 meters, and above 600 meters we can choose a hybrid combination with the back span as concrete and the main span as steel, and it turns out to be economic. So next, we move on to the preliminary and calculations for initial section selection. So once we have selected the bridge geometry, the initial deck section and material in the previous step, we need to perform preliminary calculations to calculate the initial forces in the cables, pylon and deck to finalize their section for the first iteration. These calculations can be easily done with hand. The axial forces in cables, deck, and pylon can be calculated for an articulated system. To explain this, I will take this bridge as an example. So this is a typical symmetric twin pier cable stayed concrete bridge. Here SB represents the back stay and SF represents the front stay. The permanent load is assumed to be 128 kilonewton meter that we can see over here, and the live load is assumed to be 11.5 kilonewton per meter that we see over here, with a concentrated load of 375 kilonewton per meter. So let's first size the backstay cables. For permanent loads, it can be seen that only part D, this part, will go into the backstay. Part A will go directly into the anchor pier, and part B and part C will balance each other. The vertical reaction in the anchor pier can be calculated by equating the moment about the pylon hinge to be 0. So if we write the equation, we get the value of R equal to 3000 kilonewton. Now the backstay force can be calculated by dividing R by sine of the cable angle. So if we divide 3000 by sine 26.6, we get the backstay force as 6700 kilonewton. For live loads, additive backstay tension force will be generated when live load is placed in the center span, and subtractive backstay compression force will be generated when the live load is placed in the backspan. We can calculate the additive and subtractive backstay force due to live load by placing the live load in front span and back span and equating the moment to 0 about pylon hinge, same as we did for the dead load. Hence, if we follow the same process, we get an additive tension force of 902 kilonewton. We get the anchor pier force of 902 kilonewton when we place the live load in the front span, and we get a compression of 561 kilonewton in the anchor pier when we place the live load in the back span. If we divide these forces by the cable angle, we can get an additive tension force in the backstay as 2014 kilonewton and a subtractive compression force of 1253 kilonewton. So for sizing of the backstay cable, we will have a maximum tension force of 8714 kilonewton, that is nothing but 6700 plus 2014, and the fatigue range for backstay will be the addition of the cable addition of the cable forces due to the live load. That will be 2014 and 1253 kilonewtons. That comes out to be 3267 kilonewtons. Now we can use these values to size the cables as per relevant force. So now we move on to the sizing of front stay cables. Sizing of front stay cables can be done in a similar way to backstay cables. The load in the cable due to permanent load can be calculated by dividing the permanent load supported by it by the sine of its angle. Similarly, the load due to live load can be calculated. The concentrated live load is placed on the cable anchor point to maximize the cable forces. The maximum force in the cable will be the addition of the load due to the permanent load and live load. And the load due to live load only will give the fatigue range. So over here, if you calculate the tension due to dead load comes out to be 4684 kilonewton, and the tension due to live load comes out to be 1336 kilonewton. So the maximum cable design force will be 6020, which is nothing but the addition of these two values, and the fatigue range is simply the tension in the cable because of the live load. Now again, we can use these values to size the cables as per relevant codes. Next, we move on to the normal forces in the beam and pylon. The deck compression for closely spaced cables can be approximated as a parabola and can be evaluated with this equation. The maximum compression will occur for permanent load and live load acting together. So, if we use this equation with dead load and live load acting together, the deck compression comes out to be 1100-770 kilonewton. For the concentrated live load, the maximum deck compression will occur when it is supported by the front stay cable. It can be calculated by dividing the concentrated live load by 10 of the cable angle. Over here, it comes out to be 834 kilonewton. Hence, the maximum compression in deck will be the addition of this value and this value, which comes out to be 120604 kilonewton. We can use this compression force for checking the deck section for buckling as per relevant codes. The normal force in the pylon can be estimated by equating the moment about anchor pier over here to 0. The maximum normal force will occur in the pylon when permanent load and full live load will be acting together. Hence, if we equate the moment about the anchor pier to 0, we get the compression force in the tower as 19,860 kilonewton. Now this compression force is used for sizing the pylon for buckling as per relevant codes. So next, we move on to the bending moment in the pylon. The maximum moment in pylon will occur when maximum live load is placed in the front span. What we see over here. This will lead to the maximum force in the backstay cable, and hence its maximum elongation will occur for the backstay, which will cause the maximum piling tip deflection. The horizontal displacement of the piling tip can be calculated using this formula. Here, S1 is the backstay force, S2 is the factor that converts the cable elongation into the piling tip horizontal displacement. Li is the length of the backstay and A is the area of the backstay. Here, 2014 is the backstay force we previously calculated for live load placed in the front span. Once we have the tower tip displacement delta, we can calculate the fixed end moment at the piling base with this formula. We can also calculate the tower normal force for live load in front span by equating the moment about the anchor pier to 0 like we did before. This bending moment and compression is used for sizing of the piling as per the relevant codes. Next, we move on to the bending moment in the deck. The bending moment in the deck for permanent load can be evaluated by assuming the deck to be rigidly supported on the cable anchor points. For permanent loads, we adjust the pretension in the cables such that the deck behave as rigidly supported on the cable anchor points. The assumed condition of deck on rigid supports for permanent loads is specifically applicable to concrete decks because only these moments are not subject to creep. So, if we calculate the sagging bending moment in the deck, it comes out to be 1200 kilonewton meter. The sagging moment in the deck will be increased by the live load, and the live load moments need to be evaluated. The live load moments can be evaluated by assuming an equivalent system of beam on elastic foundation, or we can make a linear analysis model of the deck with spring supports at cable anchor points. So basically, we can replace these fixed supports with spring supports. The stiffness of the spring supports is estimated using Un's equation based on the assumed cable area and cable force as calculated in the previous step. The dead load of the deck is turned off in this model because we have already calculated the dead load moment. Now we can run live load on this model and estimate the live load moments. Here I have used beam on elastic foundation analogy, and hence using that I get the live load moment of 3088 kilonewton meter. Once we have the live load moments from either of the method, we can check the deck section for the permanent load and live load moment and can refine the deck section if required. So, once we have finalized the geometry and the initial sections of cable, pylon, and deck, we can go for construction stage analysis to determine the initial cable pretension to get the desired bending moment in the deck and pylon for permanent loads. Let us call the bridge configuration with desired bending moments and deck profile for permanent loads as final system for simplicity. The initial cable pretension here refers to the pretension we need to give in the cable during installation. Please note that the cable force will be different compared to these in the final system. We can also get the pre-camber at which the deck segment shall be installed to get the required deck profile for permanent loads. We can also get the variation in the cable force and deck and pylon movements during construction. So the first step that we need to do is to determine the cable forces in the final system that will give us the desired bending moment in the deck for permanent loads. We can also determine the cable forces for desired deck profile, but the deck profile is not of real importance because it can be easily adjusted using pre-camber of deck during construction. So, if we have a cable stayed bridge, and once we have finalized the initial cable, pylon, and the deck cross section, and if we make an analysis model and do the analysis for permanent loads, assuming an initial cable pretension in the cables, we will get a bed, we will get a bed deflection. Sorry, we'll get a bed deflection and bed bending moments, and we'll get some cable forces. Now, obviously, we don't want this bending moment. The deflection is not important as explained earlier because we can always adjust the deflection using pre-camber of the deck elements during casting. Now, we can optimize the cable forces so that we get the required bending moment in the deck. The optimization starts with analyzing single load cases for each cable stressing. These load cases should be scalable load cases. We stress the first cable in one load case, and then the second in the second load case, and then the third, and so on. We stress all the front cables, and in the end, we stress the back cables in the last load case. So now that we have 8 scalable load cases, we can choose 8 targets. We can choose bending moments, or we can also choose deflections. If we wish to choose bending moments, then we can choose the bending moments we had calculated previously for permanent loads, assuming the deck to be supported on rigid supports while estimating the initial deck section. Or if we choose deflections at cable anchor points to be 0, we will automatically get the desired bending moments. So here we will choose deflection at cable anchor points to be 0 and the deflection at the pylon tip to be 0. So this is what we want. Now we can build an equation system for these 8 scalable load cases and can solve it to give us the pre-stress load factors. In Sophistic, we can do it with the CSM optimization tool. So here we can see the system of equations. On the left hand side, we will have the initial pretension factors that we want to calculate, and on the right hand side over here, we have the required deformation or force targets that we provide. If we run the analysis with the initial assumed pretension multiplied with these load factors again, we can see that we get the required deck and piloted deflection, that is zero, and also the required bending moment in the deck. And we can also get the final cable forces. The assumed condition of deck on rigid supports for permanent loads is specifically applicable